everyone, and welcome to today's Explainer. To all the environmental science students tuning in with us, grab your notes and get ready, because today we're tackling a topic that is honestly as fascinating as it is deeply concerning. We spend a lot of time in this field talking about massive, highly visible ecosystems, right? Forests, oceans, the atmosphere. But today, we're going to flip that. We're going to look at the world through a microscopic lens to understand a completely invisible systemic threat. We're going to trace the life cycle of a brand new class of global pollutant. So let's map out the ultimate, unintended journey of the modern age. To really wrap our heads around this, I want you to picture a protagonist. But our protagonist isn't an animal, and it's not a person. It's a single, microscopic fragment of a discarded PET plastic water bottle. Let's just call it the Hitchhiker. Now, you might be wondering, how does this tiny hitchhiker, born on a hot, paved city street, manage to travel literally thousands of miles, completely bypassing our waste management systems, to eventually lock itself inside the most remote, pristine Arctic ice on the planet? Or, honestly, worse, how does it end up inside the cells of your own body? Today, we are going to follow its incredible, and yeah, kind of terrifying, global transit journey. Okay, let's dive into this. To understand our tiny hitchhiker, we first have to understand the macro scale of the environment it was born into. Get this. In 2023, global plastic production actually surpassed 410 million tons. That's a massive number, and 2/3 of that is made up of short-term use products. But here's the kicker, the part we really need to focus on. Statistics show that nearly 22% of this plastic waste is improperly disposed of every single year. It's abandoned in unmanaged dumps, or it just leaks directly into our environmental systems. That massive, overwhelming volume, that is the starting point for our hitchhiker's journey.
When that plastic bottle is tossed out into the environment, it doesn't just magically vanish. It breaks down, it shrinks. We define microplastics as particles ranging anywhere from 1 nanometer up to 5 millimeters in size. And the reason our hitchhiker is so incredibly successful at traveling the globe is purely because of its chemistry. These fragments are highly chemically stable and stubbornly resistant to decomposition. But more importantly, as they shrink down to the micro and nanoscale, they actually gain the ability to effortlessly penetrate biological barriers. It's like they have a master key to living systems.
All right, let's move to Section 1. Breakdown mechanisms, specifically looking at the sun and microbes. So how exactly does a chunky plastic bottle shrink down into this resilient microscopic hitchhiker? Well, it starts with an attack from the sky. Plastic polymers like PET contain carbon-hydrogen bonds, and the energy of these chemical bonds is actually lower than the energy of ultraviolet light. So when our plastic bottle is just sitting there baking in the sun, UV rays bombard it, literally snapping those CH bonds apart. This triggers a violent chemical chain reaction, generating these high-energy hydroxyl radicals that continuously cleave the polymer's main chain. Basically, the surface of the plastic begins to erode, oxidize, and physically crack open, shedding tiny microplastic fragments out into the environment. Once the UV light has roughened up the surface of our hitchhiker, it creates these tiny, microscopic cavities. And this new, porous surface texture becomes absolutely prime real estate for microorganisms. Pioneer microbes from the surrounding soil or water latch right onto the plastic. They secrete enzymes that cause biofragmentation, actively breaking the PET down even further into smaller compounds. Things like terephthalic acid, which the microbes can actually assimilate into their own metabolic pathways. And this brilliantly illustrates that whole biological breakdown process. We start with a bare microplastic fragment, which is then colonized by pioneer microbes to form a rich, complex microecosystem right there on the surface. It's pretty wild. Through microbial metabolism, some of the plastic is absorbed as energy while the rest is converted into byproducts like carbon dioxide, water, and methane. So, at this point, our hitchhiker isn't just a piece of trash anymore. It is literally a mobile, microscopic habitat. Okay, moving right along to Section 2, the transit network, taking us from urban to polar environments. Now that our hitchhiker has been broken down and heavily conditioned by the elements, it is ready to travel. Wind and temperature variations act as the engines here, providing the flights for our massive transit system. Microplastics from urban suspended particles, factory exhaust, and, this is a big one, incredibly common sources like tire wear dust catch these air currents. They undergo massive horizontal migration across the atmosphere, eventually falling back down to Earth through wet deposition, like rain and snow, or just dry deposition, settling on the ground. If we compare a few different environments, the ubiquitous, boundaryless nature of this network becomes pretty staggering.
Urban air is heavily congested with these particles, mostly due to local emissions and tire dust. But because of global atmospheric circulation, researchers have found surprisingly high concentrations of microplastics in completely isolated, untouched regions, like pristine Arctic snow. Think about that for a second. Our hitchhiker literally caught a flight on the wind from a dense, polluted city, only to be deposited by a snowflake at the very top of the world. Crazy, right?
Now, when it doesn't take to the sky, it takes the highways. Rain washes our urban hitchhiker right into surface runoff, rivers, and lakes. And even though our wastewater treatment plants do a good job filtering out a lot of this, the sheer volume of water means millions of particles bypass filtration entirely. So the rivers act as these massive, unstoppable conveyor belts, ultimately flushing our hitchhiker straight into the ocean, where deep ocean currents can carry it to entirely new continents.
But hey, don't let the ocean get all the attention here. Terrestrial systems actually hold 4 to 23 times more microplastics than marine environments. Between agricultural films, sewage sludge that we use as fertilizer, and atmospheric deposition, our hitchhiker easily infiltrates the soil. And once it's there, it causes real problems. It alters soil porosity, binds to aggregates, and severely disrupts the lives of soil microorganisms and earthworms, which, as we know, are absolutely crucial for our agricultural health.
Section 3, Bioaccumulation and Entering the Food Chain.
So our hitchhiker has traveled the sky, surfed the rivers, and buried itself deep in the soil. But its journey is far from over. Its final destination is inside living biology. There are a few major entry points for this infiltration. In the soil, plants actually absorb submicrometer plastics directly through their roots via a crack entry mode. In the oceans, keystone species like plankton and krill accidentally ingest them. Filter feeders like mussels and oysters pump them straight into their tissues. And because our hitchhiker is just too tough to digest, it bioaccumulates. It moves steadily up the food web, from krill to fish, and eventually right onto our dinner plates in the form of seafood, sea salt, and even the vegetables we grow.
Moving into Section 4, Human Health Risks, looking specifically at the bloodstream and urban lung risks.
This brings us to the most intimate and frankly alarming phase. What happens when the systemic ecological infiltration becomes a human physiological reality? So the crucial point is this. Humans are no longer just outside observers, we are fully integrated into the microplastic circle. We're exposed to our digestive tract via the food and water we just talked about, and even through our skin. But for urban populations constantly surrounded by airborne tire dust and synthetic fibers, the respiratory pathway is massive. Studies actually show that the amount of microplastics entering our bodies through inhalation can be 3 to 15 times greater than through ingestion.
When you inhale a microplastic fragment while walking down a city street, a microscopic battle kicks off in your lungs. Particles under 10 micrometers are immediately attacked and engulfed by macrophages. That's your immune system's cleanup crew, which leads to chronic inflammation. But if the particle is under 1 micrometer, we're talking about a nanoplastic. And those, they can pierce right through the lung epithelium, triggering intense immune responses, elevating pulmonary arterial pressure, and eventually slipping directly into your circulatory system.
Which leads us to a truly chilling scientific milestone. Back in 2022, Leslie and colleagues definitively discovered and quantified plastic particle pollution in human blood. Let that sink in. Your bloodstream is basically a physiological superhighway. Once our hitchhiker is in the blood, it has a fast-track transport system that allows it to rapidly reach secondary organs. Animal studies have already shown these particles accumulating in the liver, the kidneys, and the intestines, causing lipid metabolism disorders and totally disrupting our delicate gut microbiomes.
And the danger here is twofold. First, you have direct tissue damage. These foreign particles cause physical irritation, they generate reactive oxygen species, and they can even cause DNA strand breaks. But then there is the synergistic toxicity. Remember how the sun and the microbes made our hitchhiker porous way back at the start? Well, that makes it act like a microscopic sponge. As it travels through the environment, it absorbs heavy metals, persistent organic pollutants, and antibiotics. So when it finally enters your cells, it brings all those highly toxic passengers right inside with it.
And finally, Section 5, the ecological threat as a systemic issue.
So we've tracked our hitchhiker from a macro piece of street litter, watched it get broken down by UV rays and microbes, swept up in a massive global wind and water transit system, all the way to its final resting place inside human tissue. This is the new reality of environmental science, guys. We're not just talking about a localized oil spill anymore. It's about a persistent global circulation of synthetic matter. Which leaves us with this final thought to ponder as you continue your studies. The hitchhiker is no longer just out there in the environment. It is in here, with us. If we are now permanently woven into this global microplastic circle, literally sharing our biology with synthetic polymers, how will decades of this long-term synergistic exposure fundamentally reshape the future of both human health and the Earth's ecosystem biology? I really think it's the defining environmental question of our generation, and I absolutely encourage you all to keep seeking the answers. Thanks so much for joining me on this explainer, and I'll catch you next time.